Hello everyone and welcome back to Mathematical Mindset. So right here on our previous video on matrices, we talked about the transpose of a matrix. So in today's video, we are going to look at the special matrices and their properties. Okay, so the first special matrices we have is the identity matrix or the unit matrix. It's a square matrix where all the diagonal elements are 1 and all of diagonal elements are 0. Now when we talk about diagonal elements, this is what it refers to as diagonal elements. So if all the diagonal elements are 1 and the off diagonal elements are 0, we refer to this as an identity matrix. And this is a 3 by 3 identity matrix. Also, this is a 2 by 2 identity matrix when you have 1 0 and 0 1. And if you take a look at this, you find out that the diagonal elements are 1. Alright, so this is what it simply implies by identity matrix. So the properties, this acts as a multiplicative identity. Now what does it simply imply? It implies that if you multiply any matrix with this identity matrix, it is equal to that matrix. That is what it means. Now this implies that if we have a 2 by 2 matrix, let's say 2 3 4 5, multiply a 2 by 2 identity matrix which is 1 0 0 1. So if we multiply the both of them, we're going to have this to be, so let's simply try this right here. So multiplying this, we have this to be equal to 2 multiply 1 is 2 plus 3 multiply 0 is 0. Then we come here, 2 multiply 0 is 0 plus 3 multiply 1 is 3. Then we have 4 multiply 1 4 plus 5 multiply 0 is 0. 4 multiply 0 0 plus 5 multiply 1 is 5, and this is equal to 2 3 4 5, and which is the same as the what? The matrix A. So that is what it means for the identity matrix to act as a multiplicative identity. Now the second property says that the determinant is always 1. If you find the determinant of a 2 by 2 identity matrix or either a 3 by 3 identity matrix, this determinant will always give you 1. In the next video, I'm going to talk about the determinant of a matrix, and I'm going to use the identity matrix as one of the examples to find the determinant of a matrix. So you want to stay tuned for the next video. And lastly, the inverse of the identity matrix is the identity itself. So if you take the inverse of an identity matrix, it's going to give you the identity what? Matrix. Number 2, we have the diagonal matrix. Now, a square matrix where all non-diagonal elements are 0. So a diagonal matrix simply implies that now this is a diagonal matrix, right? Now, since the diagonal elements are non-zero and all the non-diagonal elements are 0, we refer to this type of matrix as a diagonal what? Matrix. Now, one of the properties states if D is a diagonal matrix, then D raised to the power of n is obtained by raising each diagonal element to n. That is to say, if we have this to be a diagonal matrix, then if we are to solve for D raised to the power of 2, you can easily obtain this by raising each of the elements to 2. That is what it implies. Number 2, the determinant is the product of the diagonal elements. Now, the determinant of this matrix is going to be the product of the diagonal element. That is to say, 5 times 3 times 2. We have this 5 times 3 is 15, 15 times 2 is 30. So if you look for the determinant of this diagonal element, you are going to have 30. That is what it implies. So guys, try this out and leave a comment below in the comment section. Number 3, the inverse exists if all diagonal elements are non-zero. Alright, so if all the diagonal elements, which is 5, 3, and 2, are non-zero, then this diagonal matrix has an inverse. That is what it implies. Number 3, we have the upper triangular matrix, a square matrix where all elements below the main diagonal are 0. Now, this is the diagonal. Alright, 2, 5, and 7 is the diagonal matrix right here. Alright, so if all the elements below the main diagonal are 0, we refer to this as the upper triangular matrix. So we have 0 here, 0 here, 0. So these are the elements below the main diagonal and they are 0. So we call this an upper triangular what? Matrix. Now the properties, the determinant is the product of the diagonal elements. That is 2 times 5, 10, 10 times 7 is 70. So if you look for the determinant of this matrix, you are going to have 70. That is what it implies. Multiplication of 2 upper triangular matrices results in an upper triangular matrix. That is to say, if you multiply 2 upper triangular matrices, the result will be an upper triangular what? Matrix. Number 4, we have the lower triangular what? Matrix, a square matrix where all elements below the main diagonal are 0. Alright, so this is the main diagonal right here. Now the elements above, which is 0, 0, 0. As you can see, they are all 0. We refer to this type of matrix as a lower triangular what matrix. Now, this lower triangular matrix shares the same properties with upper triangular what matrices. Number 5, we have, as you can see, it is equal to that same matrix. So hence, this matrix is called a symmetric matrix. That is what it implies. Now, the properties, the eigenvalues of a symmetric matrix are always real, and the sum and product of two symmetric matrices of the same order are also what symmetric. That is, if you take the sum and product of a symmetric matrix, the answer will also be a symmetric what matrix. Number 6, we have the skew symmetric matrix, a square matrix whereby the transpose of A is equal to negative A. That is to say, if we take the transpose of K, this is going to give us a negative matrix A. Alright, so let's try this right here. So if you take the matrix, we have this to be 0, negative 2, negative 4. Then we have this to be 2, 0, and negative 6. We have here to be 4, 6, and 0. Alright, now let's simply check if this is correct. Now let's simply multiply this matrix with negative. Alright, so if you multiply negative times 0, we give us 0. Negative plus negative is positive 2. Negative multiply negative 4 will give us 4. Negative multiply 2 is negative 2. Negative multiply 0 is 0. Negative multiply negative 6 will give us 6. Negative multiply 4, negative 4. Negative multiply 6, negative 6. Negative multiply 0 will also give us what? 0. Guys, as you can see right here, we have been able to prove that if you take the transpose of a square matrix, we are going to have negative A of that matrix. Then this simply implies that this type of matrix is called a skew symmetric matrix. Now, the properties, the diagonal elements are always 0, and the eigenvalues are either 0 or purely imaginary. That is what this implies. Number 7, we have the orthogonal matrix, a square matrix where the A transpose multiply a matrix A is equal to A multiply a matrix A transpose. This is equals to an identity matrix, meaning its transpose it is inverse. That is what it means. So let's try out this matrix here that says 0, 1, negative 1, 0. So we're going to take the transpose of this. The transpose of this will be 0, 1, negative 1, and 0. So if we multiply the two of them, let's check if we're going to have an identity what? Matrix. Okay, so 0 multiply 0 is 0, plus 1 multiply 1 is going to give us 1. 0 multiply negative 1 is 0, plus 1 multiply 0 is 0. Negative 1 multiply 0 is 0, plus 0 multiply 1 is 0. Negative 1 multiply negative 1 is going to give us positive 1, plus 0 multiply 0 is 0. Okay, so this is equal to 0 plus 1, 1, 0 plus 0, 0, 0 plus 0, 0, and 1 plus 0 is 1. Guys, as you can see, we have been able to verify this right here. And this gives us a 2 by 2 identity what? Matrix. So I'm just going to put out the answer right here, which is 1, 0, 0, 1. Okay, so this is it right here. So this to show you that if you take the transpose of any matrix and you multiply it, it's going to give us an identity matrix, and this type of matrix is called the orthogonal what? Matrix. Now, the properties, the determinant is always plus minus 1. The columns or row form an orthonormal basis. The columns or row it form an orthonormal basis. So that is all about the orthogonal matrix. Next, we have singular and non-singular matrices. A singular matrix, a square matrix whose determinant is 0, meaning it does not have an inverse. So I'm just going to quickly solve this right here to show that this is a singular matrix. If you take the determinant, this is going to multiply this and this will multiply this, right? So we have this to be 4 times 1 subtracting 2 times 2. 4 times 1 is 4 minus 2 times 2 is 4. This is equals to 0. Now this implies that this is a singular matrix. If the determinant is 0, then that type of matrix is called a singular matrix. Then a non-singular matrix is a square matrix whose determinant is non-zero. And if the determinant of a particular matrix is non-zero, then it has an inverse. So if you try this right here, that is this, we multiply this and this will multiply this. So we have 4 times 2 minus 3 times 1, 8 minus 3, and this is equals to what? 5. So since the determinant is non-zero, then this type of matrix is called a non-singular matrix. Number 9. Nilpotent matrix. A square matrix A is nilpotent if A raised to the power of k is equals to 0 for some integer k. Now this simply means any matrix can be A raised to the power of 5, it must be what? 0. Now let's try out this matrix. We have n, which is a matrix n, which is 0, 1, 0, 0. So we have that if we take n raised to the power of 2, and we say that if A raised to the power of k is 0, that is, if any matrix is raised to the power of k for any integer, then that matrix is 0, 0, 0, 0. That is what it means by a nilpotent what matrix. And the properties is the eigenvalues are always what? 0. Number 10, we have the emitting and skew-emitting matrices. Now the emitting matrix says if A raised to the power of h is equals to A, that is the conjugate transpose is equal to the matrix itself. That is what it means. Then the skew-emitting matrix implies that if you take the conjugate transpose of a matrix, it is equal to a negative matrix. It's equal to the negative what matrix. This type of matrix are for complex matrices, but we are going to talk about the emitting and the skew-emitting matrices as the video goes on. Number 11, we have the stochastic matrix. This is a matrix where all entries are non-negative and each column or rows sums to 1. If we add 0.5, 0.3 and 0.2, if you add each row, you will have 1. If you add each column, you are going to have 1. That type of matrix is known as the stochastic matrix. So guys, these are the types of special matrices and their properties right here. So with this guys, I'm going to see you in the next video where I'm going to talk about how you can find the determinant of a 2x2 matrix and a 3x3 matrix. So with this guys, I'm going to see you in the next video. And guys, if you want to get notified for any of this video or matrices, do not forget to subscribe to Mathematical Mindset, turn on your post notifications so that you get notified. So with this guys, bye and see you in the next video.